the fascinating connection between quantum computing and time travel. Just the idea of it sends shivers down our spines. Imagine stepping into a machine, pressing a button, and suddenly finding yourself in the past or the future. Would you witness the birth of civilizations, prevent disasters, meet historical figures? Or would you accidentally change something so small that the entire course of history shifts? The concept of time travel has fascinated humanity for centuries, appearing in myths, literature, and blockbuster films. But is it just science fiction? Or could there be a real scientific basis for it? And here's the big question. Could quantum computers, those mysterious machines that harness the bizarre laws of quantum mechanics, be the key to unlocking time travel? For centuries, humanity has been captivated by the idea of time travel, whether through H.G. Wells' The Time Machine, the iconic Back to the Future films, or modern sci-fi epics like Interstellar. While once considered pure fantasy, recent breakthroughs in quantum physics and computing have reignited the debate. Could time travel actually be possible? Unlike the mechanical time machines of fiction, the key might lie in the bizarre and counterintuitive world of quantum mechanics. Quantum computers, which harness the strange behaviors of particles at the subatomic level, could provide the tools needed to manipulate time in ways previously thought impossible. But how? To answer that, we must first explore the fundamental principles of quantum mechanics and how they challenge our classical understanding of time, causality, and reality itself. The journey from science fiction to scientific possibility is not straightforward. It requires us to rethink the very fabric of space-time, the nature of cause and effect, and the limits of technology. While we are still far from building a working time machine, the theoretical groundwork is being laid in labs around the world. Researchers are already simulating time loops, testing retrocausality, and probing the boundaries of quantum entanglement, all in the hope of uncovering whether time travel could one day become a reality. This exploration is not just about satisfying curiosity. It could revolutionize computing, communication, and our understanding of the universe. So let's dive into the science behind quantum time travel and examine whether the future of temporal manipulation lies in quantum computers. Now, how does this relate to time travel? Some theories suggest that the peculiar behavior of quantum particles might allow for a form of retrocausality, where an effect precedes its cause. In other words, events in the future could influence events in the past. This idea isn't as far-fetched as it sounds. In 2017, scientists at the University of Queensland conducted a simulation showing how a quantum particle could theoretically travel back in time by exploiting quantum superposition and entanglement. While this doesn't mean we'll be building DeLoreans anytime soon, it does open the door to the possibility that quantum computers could manipulate time in ways we don't yet fully understand. Another intriguing avenue is the concept of closed time-like curves, CTCs, hypothetical pathways in spacetime that loop back on themselves, allowing for time travel. Renowned physicist David Deutsch proposed that quantum computers could simulate CTCs, effectively creating a computational model of time travel. In this scenario, information, rather than physical objects, could be sent backward in time. While this doesn't mean humans could hop into a time machine, it suggests that quantum computers might enable a form of digital time travel where data from the future could be accessed in the present. Of course, all of this remains speculative. The laws of physics as we know them, particularly Einstein's theory of general relativity, allow for theoretical time loops, but they also introduce paradoxes like the infamous grandfather paradox. What happens if you go back in time and prevent your own birth? Quantum mechanics might offer a way around these paradoxes through the many worlds interpretation, which suggests that every possible outcome of a quantum event spawns a new, parallel universe. In this view, time travel wouldn't rewrite history, but instead create a branching timeline, avoiding logical inconsistencies. So could quantum computers make time travel possible? The answer is still uncertain, but the theoretical groundwork is being laid. As quantum technology advances, we may find new ways to probe the boundaries of time itself. In the next part, we'll dive deeper into the experiments and breakthroughs that are bringing us closer to answering this mind-bending question. Breakthroughs in experiments. Are we closer to quantum time travel? The idea of time travel has always been shrouded in mystery, but recent advancements in quantum computing are making scientists take the concept more seriously than ever before. While we're still far from sending humans through time, researchers are exploring how quantum mechanics could allow information, or even particles, to traverse time in ways that defy classical physics. So what are the key experiments and theories pushing the boundaries of this possibility? One of the most fascinating developments comes from quantum simulations of time travel. In 2014, a team at the University of Queensland, led by physicist Tim Ralph, designed an experiment to simulate how a photon, a particle of light, might behave if it could travel back in time. Using quantum entanglement, they created a scenario where the photon's state appeared to influence its own past, a phenomenon known as retrocausality. Essentially, the experiment suggested that, at a quantum level, cause and effect might not always follow the linear timeline we're used to. This doesn't mean we've cracked time travel, but it does show that quantum mechanics allows for effects that look like time reversal under controlled conditions. Another groundbreaking study came from the University of Vienna, where researchers used quantum optics to simulate a hypothetical time loop. By manipulating entangled photons, they demonstrated how information could, in theory, be sent backward in time without violating the laws of physics. The key here is that quantum systems don't always obey the same cause and effect rules as the macroscopic world. Instead, they operate in a probabilistic, nonlinear fashion, opening the door to strange possibilities, like a quantum computer sending a calculation result before the calculation is performed. But how could this translate into actual time travel? One compelling idea is that quantum computers might one day manipulate space-time itself. According to Einstein's general relativity, massive objects warp space-time, creating gravity. Some physicists speculate that if we could control quantum fields with enough precision, we might be able to create tiny localized distortions in space-time, effectively forming microscopic time tunnels. These wouldn't be the kind of portals seen in movies, but they could allow for the transfer of quantum information across time. Perhaps the most radical proposal comes from the concept of post-selected time travel, proposed by physicist Seth Lloyd. He suggested that by carefully selecting quantum states after an experiment, a process called post-selection, researchers could simulate a scenario where information appears to have traveled backward in time. In 2011, Lloyd and his team demonstrated this in a quantum optics experiment, showing that post-selection could mimic the effects of a time loop. While this doesn't mean we're building time machines, it does suggest that quantum computers could one day perform operations that look like time travel from a computational standpoint. Of course, all of these experiments come with major caveats. For one, they rely on highly controlled quantum systems, not macroscopic objects or people. Secondly, they often involve interpretations of quantum mechanics that are still debated, such as the many worlds interpretation or retrocausal quantum theory. And then there's the biggest obstacle, the sheer energy requirements. Warping space-time, even on a tiny scale, would require energies far beyond our current technological capabilities, possibly even needing exotic matter with negative energy, something we've never observed in nature. Yet despite these challenges, the progress is undeniable. Quantum computers are already solving problems that classical machines can't, and as they grow more powerful, they may allow us to test increasingly bold theories about time. Some researchers even believe that quantum networks, future versions of today's quantum internet, could enable forms of time-encoded communication where data is transmitted in ways that appear to break conventional causality. So, are we closer to real-time travel? The answer is both yes and no. We're not yet at the stage of sending people or objects through time, but we are uncovering the fundamental mechanisms that could make some form of time manipulation possible. The next frontier? Bridging the gap between quantum simulations and real-world applications, which we'll explore in the final part of this discussion. Exploring the quantum realm. If time travel is ever going to move from science fiction to reality, the answer might lie in the bizarre and counterintuitive world of quantum mechanics. This is the realm where particles can be in two places at once, where cause and effect don't always follow the rules we expect, and where the very fabric of reality seems to twist in ways that defy common sense. Could these quantum phenomena hold the key to unlocking time travel? And if so, how close are we to making it happen? Let's start with one of the strangest aspects of quantum mechanics: entanglement. When two particles become entangled, their properties are linked no matter how far apart they are. Change one, and the other instantly changes, even if they're light years apart. Einstein called this spooky action at a distance, and to this day, it challenges our understanding of space and time. Some physicists speculate that entanglement might hint at a deeper structure of reality, one where time isn't as linear as we think. Could we somehow exploit this phenomenon to send information, or even matter, backward in time? Then there's quantum superposition, the idea that particles can exist in multiple states at once until they're observed. Schrödinger's famous thought experiment, where a cat is both alive and dead until you open the box, illustrates just how weird this gets. If particles don't have to choose a state until they're measured, does that mean the future is already influencing the present? Some interpretations of quantum mechanics, like the transactional interpretation, even suggest that quantum events involve signals moving both forward and backward in time. If that's true, could we amplify this effect to create a real time travel mechanism? Another mind-bending concept is the idea of closed time-like curves, CTCs, theoretical paths through space-time that loop back on themselves, allowing time travel to the past. General relativity doesn't forbid them, but they require extreme conditions, like the intense gravity near a black hole or exotic matter with negative energy. The problem? We don't know how to create or stabilize them, but here's where quantum computers might come in. Quantum computers don't just calculate faster, they explore all possible solutions to a problem at once. This makes them uniquely suited for simulating complex quantum systems, including hypothetical space-time structures like wormholes or CTCs. In 2019, researchers at the University of Queensland used a quantum processor to simulate a quantum particle traveling back in time. Of course, this wasn't actual time travel, just a simulation of how it might work under quantum rules, but it showed that quantum computers could help us test theories that would otherwise be impossible to study. One of the biggest obstacles to real-world time travel is decoherence, the tendency of quantum systems to lose their delicate states when interacting with the environment. Quantum computers struggle with this too, requiring near absolute zero temperatures and error correction just to function. If we can't even keep a few qubits stable, how could we hope to manipulate space-time itself? Yet progress is happening. Companies like Google, IBM, and startups in quantum research are making breakthroughs in error correction, qubit stability, and scalability. Some physicists, like David Deutsch at Oxford, argue that once we have fully error-corrected large-scale quantum computers, we might be able to run simulations that reveal entirely new physics, perhaps even the secret to bending time. But even if the physics checks out, the philosophical and ethical questions remain. If time travel is possible, even in a limited way, what does that mean for free will, for destiny, for the nature of reality itself? And if we could send information back in time, should we? The grandfather paradox is just the beginning. What if changing the past erases the very future that invented time travel in the first place? The future of time travel. Could quantum computers rewrite reality? As we stand on the frontier of quantum computing and theoretical physics, the question of time travel shifts from pure science fiction to a tantalizing scientific possibility, albeit one still shrouded in uncertainty. If quantum computers continue to evolve at their current exponential pace, could they eventually unlock the secrets of time manipulation? And what would that mean for our understanding of reality itself? Quantum computers as time machines? Some of the most daring theories suggest that quantum computers might not just simulate time travel, they could become time machines in a limited sense. How? By exploiting the fundamental nature of quantum mechanics, where information doesn't always follow the arrow of time as we perceive it. One provocative idea comes from the field of quantum teleportation, where the state of a particle is instantaneously transferred across space using entanglement. Researchers have already demonstrated this over distances exceeding 1,000 kilometers. Now imagine if this process could be adapted to time instead of just space. A team at the University of Oxford proposed that, in theory, quantum teleportation protocols could be modified to send quantum information backward in time. This wouldn't be a physical time machine, but it would mean that data, perhaps even encrypted messages, could be sent into the past under the right conditions. Another mind-bending concept is quantum time crystals, a phase of matter that repeats in time rather than space. First theorized by Nobel laureate Frank Wilczek and later observed in lab experiments, time crystals exhibit motion without energy input, effectively ticking indefinitely like a clock without being wound. Some physicists speculate that if we could control these structures at a large enough scale, they might serve as a scaffold for manipulating time itself, creating stable loops where quantum states cycle in ways that mimic time travel. The grandfather paradox in quantum solutions. One of the biggest hurdles to time travel is the infamous grandfather paradox. If you go back in time and prevent your own birth, how could you have existed to do so in the first place? Classical physics offers no resolution, but quantum mechanics might. The many worlds interpretation suggests that every quantum decision spawns a new, parallel universe. In this framework, time travel wouldn't rewrite history, it would simply branch off a new timeline. So if you went back and somehow altered the past, you wouldn't erase your own existence. You'd just create a new reality where events unfolded differently. Quantum computers, with their ability to process superpositions of multiple states, might be uniquely suited to modeling these branching timelines. Another solution comes from self-consistent time loops, where any action taken in the past was always part of history. For example, if you traveled back to give Shakespeare a copy of his own plays, those plays would have always been influenced by their future version. Quantum computers could simulate these loops, helping physicists test whether such scenarios avoid paradoxes. The energy problem and exotic matter. Even if the math allows for time travel, the engineering challenges are staggering. General relativity permits the existence of wormholes, shortcuts through spacetime, but keeping them stable would require negative energy, a hypothetical form of matter that defies gravity. While no such material has ever been observed, quantum field theory suggests that negative energy densities might be possible at microscopic scales, thanks to phenomena like the Casimir effect. This is where quantum computers could play a crucial role. By simulating exotic quantum states, they might help us discover whether negative energy is physically achievable, or if there's another way to warp spacetime without it. Some researchers even speculate that advanced quantum AI could one day solve equations we can't yet fathom, revealing entirely new pathways to time manipulation. Ethical and philosophical implications. If time travel, or even just time looping information, ever becomes possible, the consequences would be staggering. Could we prevent disasters by sending warnings to the past? Would we create infinite alternate realities every time we tweaked history? And who would control such power? Already, quantum encryption allows for unhackable communication. If time-looping data were added to the mix, it could revolutionize cybersecurity, finance, and even historical research. But it could also introduce unprecedented risks, like causal loops, where future knowledge corrupts the present in unpredictable ways. The final verdict. Are we there yet? As of now, time travel remains firmly in the realm of theory. Quantum computers are still in their infancy, and the energy requirements for space-time manipulation are beyond our reach. But the fact that serious scientists are exploring these ideas, backed by real experiments in quantum mechanics, means we can't dismiss the possibility entirely. In the coming decades, as quantum processors grow more powerful and our understanding of space-time deepens, we may find that time travel isn't magic, just physics we haven't mastered yet. Until then, quantum computers will continue to serve as our best tool for probing the edge of reality, one entangled qubit at a time. So could time travel be possible with quantum computers? The answer is still maybe, but for the first time in history, we're asking the question with equations instead of just imagination. And that alone is a revolution.